Just a very short lecture here. So when we say we fit a curve to some data, and we want to say give a measure of how high quality a fit it is. So for example, if you fit a line to this and you fit a line to this, you're going to get a higher quality fit to this. And the question is, before you even do the fit, can you measure kind of how good the fit is going to be? And this is essentially what's the correlation coefficient. So here we see, although both sets of data are well fitted by the same line, it is clear that the first set of data were a high quality of fit, while the second will be less quality. So what we do is we use the correlation coefficient. You probably will not be calculating this from first principles, but you might see it in an assessment where you have to calculate it. The formula comes here, but what you have to understand is that the closer this is to plus or minus 1, the better the fit. You might have seen this at Leaving Cert, actually. All right, let's see what kind of questions we have, or examples here. So, Tymar Engineering or civil engineering firm in the midst of expansion due to economies of scale. The cost in thousands C of training in a new employee reduces when the number of trainees T increases. In order to get an idea of how much a sector expansion will cost, the HR manager was asked to produce data on previous expansions. So it's weird that they had 5 trainees, then 10. those numbers are a bit funny. So we can examine the correlation of this. So this is the correlation of C versus 1 over T. So essentially what you'd be doing here is you'd be plotting C versus 1 over T and seeing how much of a straight line it is. Okay, so is there a question here? So if we scatter plot these, you can see that they're kind of pretty much on a straight line. If you apply the formula, which you would just do in Excel, how to do that will be a question in an assignment. You find that R is like 0.99896. That's a very, very good fit. Essentially anything above 0.9 is quite good. And you can see they're very, very close to being on a straight line. Okay, a second question here. When a force of 100 kilonewtons is applied to an object of length L0 with a cross-sectional area of 1 centimeter squared made out of an alloy with a Young's modulus of E, so it's the length is transformed. So you've got different lengths of rod, 2 meters, 4 meters, 6 meters, 8 meters, 10 meters, and a force of 100 kilonewtons is applied, and you're getting extensions here like this. You can consider the correlation of L1 with L0, and I'm not actually getting anything here, but my understanding is maybe there's a picture on the next page. Yeah, so see these, they're right on the line. So this is going to be really, really high correlation, and in fact it's equal to 1 to 5 decimal places. So all you really have to understand here is that the closer R is to 1, the better. You can get R equal to -1, and that's if it goes down. So if the slope is negative, this would be an R being negative. R equal to 0, I don't think really happens so much. You get R is undefined, which means there's no correlation.